In this video, we're going to take a look at convergence of the Lysen-Reimer binomial and Cox-Ross-Rubinstein binomial frameworks to cache or knotting binary options. And we're using Rubinstein and Reiner's closed form solution. So basically, and I'll leave a link to the code. The source of the code on the Vinegar Hill Finance Labs portal. If we go into Visual Basic here, just to take a quick look at our code, I've just slightly amended the binomial formula, the binomial VBA code based on Espen Hoag's approach here. And I've left out the array output that would yield delta, gamma, theta, and transpose. So what I want to do is to observe the effect of increasing the step size and then the speed of convergence, and compare the Cox-Ross-Rubinstein binomial against the Lysen-Reimer binomial. And we're going to use the Rubinstein cache or knotting, Rubinstein and Reiner 1991 approach, so a cache or knotting call, cache or knotting put. Okay, so we go back into the spreadsheet, and what we can do here is we can just gauge the extent to which the Rubinstein or the Reiner and Rubinstein estimate here is similar to the Cox-Ross-Rubinstein and the Lysen-Reimer approaches. So Cox-Ross-Rubinstein is the binomial approach to estimating a plain vanilla European or American option. We've adopted that here to estimate the binary option for a cache or knotting binary output, and likewise we're going to do the same here for using the Lysen-Reimer approach, and again we're adopting the framework for the binary option. Now, might be useful here just to give each the same number of digits or decimal places. Okay, so I might go 5, maybe 4, right? Just to get the ball rolling. And just to note here, so the cache or knotting call basically takes the values, the same parameter inputs as we might observe for any option, for a plain vanilla option, but then we have to specify typically how much we stand to gain in the event of the option being in the money. So for instance, if we pay 69.87 for a call option, I'm going to go with a call option here. So cache or knotting call option. If the option is in the money, we make 100 back, and the cost would be 69.87. Using Cox-Ross-Rubinstein, with only 3 steps, we would have 53 is the cost, obviously wrong, and Lysen-Reimer, obviously, well, close to true for Reiner and Rubinstein, but we have to look at the effect of increasing the step size, and perhaps we diverge away. To consider the payoff here with a cache or knotting call option, if we took those values of 110 and the strike price was 100, the risk-free rate 5%, and the cash, then we would pay 69.87 for a call option. and this is the payoff we would receive. So in the event that the option exceeded 100, there would be a payoff of 100, but note we would have paid 69.87 for the option using fair value approach, and the amount we would gain in the event of the option being in the money would be $30 net of premium. If we weren't in the money at expiration after 1 year, we would lose the premium of the 69.87. Now, obviously, if this is lower, if the current stock price is less, then the cost of investing in the strategy would be lower, and we would stand to gain more, but the chances of being in the money would be less. And likewise, if the stock price was currently 90, then it should be quite cheap to acquire the option. It would only cost 33.59 according to Reiner and Rubinstein, and we would stand to gain 66. But the chances of being in the money at expiry would be greatly reduced compared to if currently the stock price was 110. Okay, so let's investigate a little bit then the behavior here. Well, obviously with Reiner and Rubinstein, it makes no difference how we scale the time step, whether we, if we have 10, let's go with, I don't know, keep it maybe odd numbers, 7, 11, 13, 19. We can do 21, and then go 50, 100, 150, 200, and so on. Okay, so let's take these and drag across. And then obviously for Reiner, Rubinstein, it makes no difference the value of the steps in the tree. But for Cox, Ross, Rubinstein, it would. And for Lyson and Reimer, obviously also as well, it makes a difference. Now, what's in this, if we want to look at this, we could go into the arguments here. And if you like, C10, the cash amount was equal to 100. Is it a call or put? It's a call. The spot price is 110. The exercise equal to 100. The time period or maturity is 1 year. And the cost of carry is R negative Q. V is the sigma, and N is the number of steps. So we would have had 53. And then for the Lyson-Reimer binomial, if we want to look at the arguments, we have the same approach. So the same arguments are used in both cases. The only difference here for Reiner-Rubinstein, when we look at this, there's no step size. We might note that there's no step size, and that obviously has to be the case because it's a closed form solution. It's not a numerical technique. Okay, so to judge then, one way we could judge here the difference between, we could start with, first of all, looking at Lyson and Reimer. And it looks as if it's converged quite quickly. So let's go to insert and come here to the line charts. And we might consider, okay, compare. This is the Lyson-Reimer, and we can see it goes from 69.80 to 69.87, going up to 200 steps. It would appear to be closer to true. If we want to take true here, let's add in, select data, and let's edit the first series here and we'll refer to this as Lyson and Reiner. Now, if we want to compare against Rubinstein, Reiner and Rubinstein, Reiner and Rubinstein, then we should select in our series here the set of values for the going from 3 up to 200 steps. And we can see there is some divergence here, but as we increase the step size, we close off that divergence. Now, we can put here on the horizontal axis the number of steps. So let's go back into select data and then put that in edit. And then the axis, the label for the axis can be modified so that we get the number of steps. So we have 3 steps, 7 steps, 11 steps, 19 steps, and you can see we're getting quite close already within 20 steps using the Lyson-Reiner framework, and by 200 steps, not really distinguishable here from the chart. Now, okay, so we're going to include now Cox-Ross-Rubinstein. So let's right-click, select data, and we'll add Cox-Ross-Rubinstein. It's the same Rubinstein, so Cox, Ross, and Mark Rubinstein for the 2 papers. And on the Y values will include in here CRR. Okay, and you can see straight away, and I guess we should edit also the step size. And what has happened is Lyson-Reiner is still here, but because we changed the scale here, we've basically put the blue Lyson-Reiner in with, it's just so close to the Reiner and Rubinstein that we can't distinguish it here visibly. So if I undo, that's Cox-Ross-Rubinstein, or sorry, that's Lyson and Reiner relative to Reiner and Rubinstein. And this is Lyson and Reiner, not to be confused with Reiner, Lyson and Reiner. When we include in Cox-Ross-Rubinstein, we changed the scale so dramatically that Lyson and Reiner got pushed up against the true value set out here. And that tends to suggest that Lyson and Reiner here is a much better way to model the binary cache or knotting option. If we were using a binomial approach to price these type of structures, Lyson and Reiner seem to have some advantage here. Convergence would appear at first glance, at least, to be much faster. Now we can try, for instance, putting in 100 here, just to stress test a little bit our results. And you can see that we take a look here at, if we remove Cox, Ross, and Rubinstein for a moment, right? We have Lyson and Reiner. It's very close, and at 100 steps, it's virtually indistinguishable, perhaps even at 50 steps. But if we include in, again, same experience as before, Cox, Ross, and Rubinstein, there does appear to be some convergence, but then we note that as we increase our step size, the level of convergence starts to disimprove, and that's not unusual with segments of sections of Cox-Ross-Rubinstein when we look at convergence behavior. Again, Lyson and Reimer would appear somewhat better. Let's go with 90 for a moment. Before I do that, let's go back to where we were. Right. So we would appear to have all three. Right. Okay, so we have this would be 110. Right, and Lyson and Reimer somewhere buried in here. If I remove this one, we will have Lyson and Reimer. Okay, so all three are here. Let's change the spot price to 90, and then we'll drag across. And again, Lyson, Cox, Ross, Rubinstein seems to be quite far. If we remove this, you can see with Lyson and Reimer, Convergence is much closer more quickly. But there is a change here in the scaling. So if we include in Cox, Ross, Rubinstein, the scaling changes, and Lyson and Reimer gets pushed up against the Reiner and Rubinstein, which here we consider to be true.